Hello everybody, my name is Cheng Sheng and I'm here to present end-to-end learning of visual inertial odometry with an EKF. What is monocular visual inertial odometry, or VIO? Monocular VIO is eagle motion estimation with one camera and IMU. Both sensors are cheap and using both can improve performance and robustness. Classical VIO methods have demonstrated tremendous success. However, they rely on manually crafted image processing pipelines, which is prone to error in rapid motion, exposure changes, and low texture environment. And failure in image processing could lead to estimator divergence. Also, classical VIO needs accurate camera intrinsic calibration and camera to IMU extrinsic calibration to function properly. We also need to tune parameters for the vision pipeline and for visual inertial fusion. Deep learning offers an alternate data-driven approach for these challenges. An example is VinEd, a fully deep learning approach for visual inertial odometry. It uses convolutional neural network to process a pair of images and two LSTMs, which is a form of recurrent neural network, one for processing high-rate IMU measurements and another for fusing IMU and vision. However, deep learning techniques work well for images that are high-dimensional in nature and has a large possibility of different scenarios that need data-driven approach. But deep learning is not necessarily required for IMU data, which is low-dimensional and have well-stood models that are grounded in physics. Our approach is to combine deep learning with classical state estimation techniques using a robocentric EKF and measurements from deep network. A IMU kinematic model is used for EKF prediction, and a learned relative poles and covariances are used for measurements for EKF update. And the entire system is trained end-to-end in a supervised fashion. Now we present the robocentric EKF formulation. The robocentric EKF uses three frames of reference. The inertial frame, it is a reference frame fixed to the Earth. The vehicle frame, which is the latest vehicle pose where the IMU is attached. And the intermediate reference frame that moves forward from one EKF iteration to the next. All poses are tracked with respect to the reference frame, and the states are divided into two parts. First, the inertial states consisting of the orientation and position of the inertial frame with respect to the reference frame, and the gravity vector in the reference frame. Second, the vehicle states consisting of the orientation and position of the vehicle in the reference frame, and the velocity, gyroscope bias, and accelerometer bias in the vehicle frame. We also have error states, which are the perturbation on the listed states. The robocentric EKF follows a three-step process, one additional step than the normal EKF. First, the prediction step, where we propagate the vehicle states using IMU data. Then the update step, which occurs after a new measurement is received and used to correct the predicted states. Finally, composition, where we move to the new reference frame by concatenating the corrected vehicle pose to the pose of the inertial frame. Then the process repeats again in the new reference frame. For EKF prediction, we have the continuous time state evolution model and the error state model for propagating covariance. These models are discretized and used in a standard EKF prediction step. For measurement, the neural network returns a relative pose measurement and covariance with each frame. The measurement residual is simply the difference between the predicted and measured relative rotation and position. The log mapping is not differentiable at pi. Thus, we use BCH approximation, which simply approximate this as subtraction of two rotation vectors. This is valid since the frame-to-frame rotation will be small. We derive the measurement Jacobian, which is then used in a standard EKF update with the residual. Finally, for the composition step, we forward the reference frame by concatenating the estimated vehicle pose to the inertial pose. The covariance also needs to be updated accordingly. For the relative pose measurements from a deep network, we adopted the deep VIO architecture, which uses FlowNet for image processing and LSTM for learning temporal dynamics. It outputs 12-dimensional vector, 6 for relative poses, and 6 for uncertainty. We assume the noise on each degree of freedom are independent, thus the covariance matrix is diagonal. We applied element-wise 10 to the power 10h to boundary uncertainty estimate, ensuring the covariance matrix is positive semi-definite. We use two loss functions to train the network. Loss function C1 is a mean square loss to train the relative pose measurement with a parameter to weigh between rotation and translation. This loss on the intermediate result is crucial for training convergence because recurrent networks are difficult to train, and this loss guides the network to learn the correct measurements. The second loss function, C2, is applied on the inertial pose, trains the overall system and the measurement covariance. We use Frobenius norm for computing error between rotation matrices to avoid the use of log mapping. Camera intrinsic calibration and camera IMU extrinsic calibration are implicitly trained as part of the network. And we use left-right flips and traveling in reverse for data augmentation. First, we tested on the KITTI dataset, which is an autonomous car dataset. To use as much data as possible, we selected one sequence for testing and the rest for training. The standard KITTI evaluation metrics are used, which is the translation and rotation error per unit traveled at 100 to 800 meter segments averaged. We compared to VNet, a purely deep learning-based method. It presents its results in box plots for 100 to 500 meter segments for sequence 10 only. And we extracted the information from the plots to the best of our abilities. We can clearly observe from the plot that our method outperforms VNet, especially at longer distances, demonstrating that our method can work better than a purely deep learning approach. From comparison to classical methods, we considered a loosely coupled formulation of stereo orb slam with multi-sensor fusion. Stereo orb slam is used because monocular orb slam has significant scale drift leading to poor results. We can see that other than sequence 1, our method outperforms the classical method on average. We also compared to trajectories obtained from just using IMU or images from our system, and the fused results have lower translation error than using each sensor by itself. Looking at sequence 7, we can see with IMU only, the estimate diverges rapidly. Note the portion of the IMU-only trajectory circled in red, which is caused by incorrect velocity estimation from error accumulation. The vehicle is stopped but slowly drifts. This problem is non-existent in our method. We can also see our method is closer to the ground truth than vision only and orb slam with multi-sensor fusion. One of the reasons that our method worked well is because of its ability to learn the covariance used for EKF fusion. Looking at the learned uncertainty from the network managed to learn a forward displacement variance that is proportional to the forward velocity. Our method has large error on sequence 1. This is because it is a highway sequence that travels up to 90 km/h, and the rest of the training data are around 40 km/h. This caused the network to underestimate the displacement consistently. We address this problem in follow-up works by including scale estimation as part of the state. We also tested on the EUROC drone dataset using RMSE error over the entire trajectory for evaluation metrics. We compared against two classical methods, monocular semi-direct visual odometry with multi-sensor fusion, which is a loosely coupled method, and VINS mono, which is a tightly coupled method. Our results are not as good as the classical methods. This is because EUROC IMU is noisy and contain large biases, and the learned measurements are not accurate enough for correcting these errors due to limited data and limitations of the deep VO architecture. Classical VO methods can be more accurate because classical VO pipelines can be up to an order of magnitude better than deep VO when corrected for scale. For future work, we can improve with more data, more accurate measurements from better performing VO architectures, and better system initialization. In summary, we proposed an end-to-end learning VIO method using RoboCentric EKF and learn relative pose measurements and covariance. Our method achieved higher performance on KITTI than classical loosely coupled VIO and purely learning-based VIO methods. And further works are required for better performance on the EUROC drone dataset. If you have any questions, please don't hesitate to ask on the CRV discussion forums or directly send me an email. The source code for this work is available on GitHub.